Hello and welcome, my dear students and my dear viewers, to today's session for revision for grade 10 and for the coming exams of term 2. Today we are revising module 6 logarithmic function. This is going to be the part 1 video for this module, and this is going to be very useful video for all my students which are going to give the exams very soon. So please watch the video till the end, revise your concepts well, and let's dive into the video. And before we start, a humble request to all my students and all my viewers who have not yet subscribed to the channel, please hit the bell icon also for notifications. So let's get started. In today's video, we are going to be covering some of the very most important questions that are for your coming exams for end of term 2. And this video, as I told you, is part 1, and we are covering module 6 logarithmic functions. Following the list of the important questions from your math book with reference to the page number and example, similar questions you should have practiced for your coming exams. They are very important. Out of this whole list, in this video I have covered only module 6 questions, which is on logarithmic functions, part 1 of the session. So let's dive into the video and start with the first question. So let's now begin with the revision of module 6 logarithmic function on my channel exclusively Mathematics Made Easy with Ms. Ruchika. So first from the list we are taking question number 1, which are the following questions 1 to 6 on your math book on page 265. So let's discuss them, and before we try to solve them, let me explain you the question here, and I want you to understand what it is asking before we start solving. For all of these 6 questions that you see on the screen, it's quite clear that the form which is given is logarithmic form. And how do you identify? You see the log written here, that's log. So this is logarithmic form which is given, and in this question you have to write the equation in exponential form. So you can very well understand that this is a question in which you will convert the logarithmic function which is given to you into exponential function. So that's your learning objective in this set of questions. And now we are going to use the basic definition for doing that. So what is that? The definition of logarithmic function is log has a base, so this is base b, and another number y, which is equal to this value of the log is equal to x. So this is the logarithmic one which is given, and we can convert it into exponential by using this formula. So b is the base, so it will remain as the base of the exponent. It will be raised to the power which is here on the right, that is x, and that whole expression is going to be equal to y. Now this expression works both ways. So if you are given in your math exam the question on log and you need to convert to exponent, you can do it this way. Or conversely, on the opposite side also, if you are given the exponential in the question and you want to convert to log, you can do other way also. So this formula is our basis for solving all of these questions that you see, and we are going to be doing them together using this formula. So just remember this conversion factor. Let's now try and solve some of them. So first question here, if you see the base is 15. So for the first part, base is 15, so b is 15. Now I'm comparing it with this expression so that I know what is my b, x and y. And then these 3 values we are going to be converting into exponential with this formula. Now what is my y? Y is 2 to 5 here, and then its whole value is given to be equal to x, which is 2. So that's our variables that we got. Now let's convert them. So this log is equal to the exponential form b to the power x equal to y. So what is b? 15. What is x? 2, and yes, 15 multiplied with 15, that's your 15 square, which is 225. So we have done the correct conversion. So this is your answer. This is exponential form. So first is done. Let's do one more out of this. So I'm going to choose now this question, question number 3. Here you see you have a fraction involved, but the formula or the method to solve is same. There is no change in that. The only value which is changed here is of the variable. So base is 5. What is y here? Y is the fraction 1 by 25 and x is the value 2. So let's use same formula, b to the power x equal to y. So base to the power x, which is here given to be equal to 2. That comes out to be equal to your y. So what is the value of y here? It is 1 over 25. Okay, so that is the expression. But if you see here 1 over 25, the expression which is given here is a fraction and the power here is positive. So it looks like as if this question has a mistake. This has to be -2 here. Be careful. Okay, so we'll convert our x to -2 and this value is also negative. Now if you try to evaluate, it will give you the correct answer, which is 1 over 25. So now this is the correct solution. Okay, let's take another one last one from the screen, which is question 6. So 3 is done. Now we proceed to 6. I'm going to give you a hint for this also. So now let's do it together. Same thing, the base is 4. The value of y here is 32 and your value of x is given in the form of a fraction. This one. So let's plug in to get our exponential form bx equal to y. This is what we are using. So b is 4. The power here is x, which is 5 over 2, and this whole thing comes up to be 32. And you can also check your answer by evaluating this value, and it will surely be coming out to be this number. So this is how you solve. Now I hope you all can try question 2, 4 and 5 similarly and work it out in your notebooks and then check your answers. Just make sure you correct this value here. It is not +2, it is -2. So there's a printing mistake on this question. Okay, so that mistake has been rectified on the screen for you and now you can check all your answers. So for question number 1 that we did today, for the conversion of log to exponential, this is the answer. Question number 2 that you must have tried yourself, converting this exponential to log, your answer is this one. And here again you notice there is -3 here, the power is negative. So it will give you a negative exponent with power negative. Question 3 has been corrected. So as I told you, there was -2 here and now yes, this is a correct answer. Similarly for question 4, the exponential form is this. For question 5, answer is this in exponent, and question 6, this is what we'd already done. So you can check all your answers. That's your answer key for the first set of questions. Okay, so let's solve now some more important questions. Now these are more higher level than the questions we've done previously, so let's do them. Now I cannot solve all questions in too much detail for you because then the video will become so long. So I'm going to select from this slide 49 and 50, and don't worry, remaining answers I will provide you, but let's do 49 and 50 together. So we'll read the question first and then we'll do them. So fx is this function defined as in log, gx is this function defined as exponential. You need to find the two composite functions here and then you need to compare and contrast them and justify your conclusion. Basically you have to see what is their value, find them, and if you feel some relationship then you have to justify and explain that relationship. Let's do this question here. I hope I'm able to solve in the space which is here for 49. So let's begin with the first composite function. So the first composite function that you need to find here is f of gx. That's how you read it. And f of gx is a composite function, meaning what? Gx is going to be the inside function, f is operating outside. So this inside function gx is actually in a way replacing your x, and you go to the function f and plug in instead of x the function gx. That's basically what it means. So I'm going to be doing the same, f of gx. So I'm replacing with function gx here, and then I go to function fx. It is already given, and I'll plug in instead of x this value of 10 to the power x. So now I'm going to be doing that. So log 10, and instead of this x, what I'm writing is 10 to the power x. Okay, so this is how you calculate composite. So there's an inside function, there's an outside function. You can plug in. I will provide the link for a video which I had made on composite functions a few months back, so you can watch that video if you want to know more about composite functions. This is quite an important function. You should all know about it. Okay, let's evaluate this log now. Log base 10, exponent 10 to the power x. So you see a pattern here. The base and the exponent's base is same. So we can definitely apply a property here, and then the power is x. So in log, when you have a power of the exponent, this power comes down. That's the power property. So x is going to come down outside the log, and it will be log 10 base 10. Now when the base and the number here are equal, the log always has value 1. It doesn't matter what is the value of the base or the number here, but they have to be equal. If they are equal, then it is always 1. So that means our composite function f of gx has come out to be x. That's the value we received for the first composite function. Let's do now the second composite function. So this is composite function 1. Now we are trying to find the composite function 2. So that is g of fx. So what is the difference here? Let's analyze. The difference here is your outside function this time is g and inside is f. That means you are going to plug in the value of fx inside this time. So I'm replacing now 10x. This is the value of fx. And now I go to function gx, which is outside, and plug in instead of x this value, 10 to the power x. Now power has to be x. So x is being replaced with this value. I hope you understand how this is working now. So let's solve this. Now this is an exponent to the power, and the power is log, and you all know the definition of log function. So we are now going to evaluate this function, and this exponent we are going to convert to log. So this becomes, when I convert the base, so base here is 10, the power here is log. So let's convert to log. So it becomes log 10 log 10x. Yes, this is the conversion. Now again, because log has the same base here also it is 10, here also it is 10, so it will get converted to 1, and eventually you are just left with x. So if you see carefully, your g of fx, even the second composite function, has come out to be the same value, which is x. What does we conclude from this? So we've got the first part, this and this. Now we need to justify the conclusion. So the conclusion says that from, say, I'm going to number this 3 and 4. From 3 and 4, we know that both the composite function, number 1 and 2, are coming out to be equal to the same value x. And that is basically the definition of inverse function. So if the composite function f of gx equal to g of fx, excuse me for writing in this space for question number 50. I'm writing here because I have less space. I will next move to a new slide for question 50. So this is the final conclusion. Both are equal and they're equal to x. And this is basically the definition of inverse function, if you remember. So this value equal to x concludes by saying that fx and gx are inverse functions. So that's our conclusion, which completes question 49. Let's move to the next slide for question 50, and after that I will give you the answer key for this screen. You can check your answers of 51 and 52. Discuss this question now. This is question 50 that we are now covering. Here you need to find the error, who is wrong. That's what you need to say, whether Betsy is wrong or Tyrone is wrong. Who's wrong? You have to find the error. So Betsy is saying that graphs of all logarithmic function crosses y-axis at this point because any number to the 0 power equals 1. This is her argument. This is what Betsy says. However, Tyrone has a different opinion. He disagrees and he says log 0 is undefined. And you have to choose who is saying the correct thing, who is correct, and you have to give reason, you have to explain your answer. That's the question. So it's a question of higher order thinking. You have to analyze and find the error. So all of you, I'll give you a hint for this question. You go to your DESMOS calculator, or you can also, if you remember the graphs of y equal to log x and y equal to e to the power x. So draw the graph of logarithmic function and exponential function and then compare them. Those two graphs, you will get your answer for this question there. And you can also observe, go a step further and observe their x and y intercepts for the two graphs. And that would be a big hint for the question. Let's discuss the answer now. Used the DESMOS graphing calculator. The link is provided on your screens. I will put it in the description box for all of you, those who want to try it out yourself. So here I have drawn for you the two graphs, one of the logarithmic function, one of the exponential function. So the graph that you see here, the red or the pink one, is for log and the blue one is for exponent. So let's compare how the graphs are behaving. So if you look at exponential graph, it is increasing and it is only meeting your y-axis. So exponential meets y-axis, quite evident. And at what point it is meeting? I have highlighted for you 0, 1. That's the y-intercept. I hope you remember from our previous lessons that exponential function is increasing, but it does not meet x-axis. Here, x-axis for exponential function is an asymptote. Means what? The graph, the blue graph of exponential looks like it is going to touch the x-axis. It is very, very close to it, but it is exactly not touching. It looks as if it's an approximation, it is close. But if you zoom further using this button, you will see that it is very close but not touching at all. So that's all about exponential function. Now let's come to logarithmic function. It is this red one which is drawn with red. Now if you see again, if I talk from here to here, it is also increasing, but then again this graph, now y-axis becomes asymptote, it's not meeting. So for y equal to log x, now y-axis is an asymptote. Means what? Again, same thing. It will look as if it is coming very, very close. It is touching, but it is not exactly touching. So it's approximately very, very close. I want you to zoom in and see that yourself. So here that means there is no y-intercept as this graph is not meeting. However, it has an x-intercept which you can see at the point 1, 0. So I hope all of you have got your answer. Who's right, who's wrong, whether it is Betsy or Tyrone. So let's now summarize the answer. Okay, so let's now discuss. So from the graph, it is quite clear that here Betsy is saying the wrong thing. Why? Because she says that the graph of all logarithmic function meets the y-axis or crosses at point 0, 1. Whereas this is the correct graph of log, which is meeting at 1, 0, not 0, 1. And it is meeting only x-axis, it is not meeting y-axis. I already told you in the last slide that y-axis is an asymptote. So the graph of log is coming very, very close but not meeting. So that's a wrong statement. And she also says that any number to the 0 power equals 1. So this is what is not correct here. Let's come to Tyrone now. Here he disagrees, and he disagrees for the right reason, because Betsy is saying the wrong statement. What Betsy said actually, that the graph meets y-axis at 0, 1, you can very well see here, is true for exponential, not logarithmic. So you can even correct Betsy here if you want, by saying that it is, what she's saying is true for exponential, not logarithm. And you can very well see that it's the same point 0, 1, and exponential graph meets at 0, 1 on the y-axis. Let's come to Tyrone now. Now Tyrone disagrees because he says log 0 is undefined. And if you see the log x graph, it is meeting only x-axis at the point 1, 0, not the y-axis, right? Why it doesn't meet y-axis? Because y-axis is an asymptote. So if you write y equal to log x, right? And here you can put log 0. So when you put log 0, y here becomes undefined. So here definitely Tyrone is quite correct, and that is justified from the graph also, because for x equal to 0 the graph is not, how is the graph behaving? Let's go. This is 0 point, x equal to 0, the graph is going down, down and down towards negative infinity, but not meeting. And the reason why this is undefined is because y-axis is an asymptote. I hope you girls are able to observe here that log x graph does not meet the y-axis at all. It does not have any y-intercept, no y-intercept. And that is the reason why it becomes undefined. So that completes the question, and we know that Tyrone is correct while Betsy is wrong. Okay, so as promised, I have given here in detail the solutions of all the questions we saw in the previous slide. 49 and 50 I've already done for you. Now you may read out and just check your answers for 51 and 52 also. So this is the continued answer key for the last question. It has different parts. So this slide also has some answers of the same question. So now let's move on to the next question. This question actually is a solved question from the book. So I've just put a screenshot here of the solution which was given in your math book. I'm just going to explain it a little bit here so that if you have any difficulty in understanding the question, you are able to get rid of that problem. Okay, so the half-life of a radioactive substance. I think you must have done this in chemistry about radioactive substances, radioactivity. So radioactive substances, as the time progresses, as the number of years goes on, they tend to decay, they tend to decrease in their radioactivity. And this pattern follows an exponential decay function, and it's a continuous function. So let's see what is given here. The half-life of a radioactive substance. So basically T1/2 is the expression that you denote for half-life of a radioactive substance. Now that radioactive substance can be, like in this question, given to be thorium-230. So this is a radioactive substance. It starts to disintegrate, to decay as time progresses. So T half exactly is the time that the radioactive substance reduces to half of its original quantity. Okay, so if the original quantity is A, original quantity means, for example, you had 100 grams of thorium-230 that you started with initially, and say after a span of 5 years only half of it is left. So that's your half-life. Half-life is your time, which is like 5 years in this case, just an example, and 1/2 of A will be the quantity which will be left. So if you want to convert this fraction into decimal, it will be 0.5 times A. So these are some basic concepts that we'll be using, and definitely because this is a question on exponential decay, so we will use the equation y equal to a to the power a multiplied with exponent to the power minus kt. Now I hope you remember what are these variables, and also one more information that is given, that the half-life is so many years. So it takes a lot of amount of years. These are 75,381. This is the half-life given to you. So many years thorium is taking to disintegrate. So there are two parts to the question, part A and B. In part A, you need to determine the value of K. So K is a constant actually, and this constant is what you need to find for this question. And since this is exponential decay, this is the exponential decay constant, you can say that. So if A is the initial amount we already discussed, then 1/2A or 0.5A is left. So Y here, which is the amount after the half-life is left, is 0.5A. A is as it is, we are taking that same value. e to the power minus k. K we don't know, that's what we have to find exactly, the constant of exponential decay, and the time or the half-life is already given, so we can plug in these values. So these are to be substituted in the equation. Now you can cancel a from both sides, it will collapse, and you are left with 0.5 equal to e to the power minus 75,381 k. Now you need the value of k which is there in the power. So what is the rule that you will apply? What is the trick? You will take log of both sides. So when you take log of both sides, the property of equality for logarithmic equation comes into function. So what we are going to be doing, log 0.5, this value on the left is as it is, and ln e is always ln e of to the power x is always x. So just the power is left, which is negative 75,381 k, and ln e vanishes. Okay. So now this is the next step. We need k, so we are going to divide both sides by this value, which is negative 75,381, and that's how you get your k. Now this k is very, very small. What does that indicate? The value of k is very, very less. It's having so many zeros, you can see 0.00000092. So this value tells you that the rate of decay for thorium-230 is very less, and that's quite evident. That's why it is taking so much time, so many years to disintegrate and be half. So now you got your k, so you can replace the k in the formula we started with. So y equal to a multiplied with e to the power negative the value of k times t. That's part A completed. Let's move to part B. In part B it says how much of a 2-gram sample of thorium-230 should be left after 1500 years. So in this one you are given the value of A. What amount we are starting with? 2 grams. So A is given to you. Also, if you see, the time is as well given. So time is 1500. So just put in these two values in the function you got from part A. We are just doing substitution, little bit of simplification and calculation. So when you do that, do the multiplication, this is what you get, 1.97. Now what does that tell you? That tells you that after 1500 years have passed, only 1.97 of grams of thorium will be remaining. So you started with 2, but after so many years passing also, since the rate of decay, the constant k that you got was very, very less, so it took a lot of time for the decay, 1500 years, and still only this much, 0.03 grams was decayed. And how much was left? 1.97. That completes the important word problem on continuous exponential decay. Okay, let's move further and come to page 274 of your math book. Question 27 to 36 are really, really important. And again, we'll be selecting a few questions out of the screen and solving. Remaining answers I'm going to give you so that you can check your solutions. So we'll try 27, that's a logarithmic equation given here. Then we'll try question 32. So these two will do, and accordingly the same method you can follow for other problems. So let's start doing question 27. Now the way I'm going to be doing 27 will be exactly same the way you will do 28. So let's write here 27. So you are given a logarithmic equation on the left, a 1 on right. What is the sign in between? Subtraction. So I'm going to combine these two and use the property of logarithm that says if you have two logs with the same base and different numbers which are subtracted, then you can combine them and write a single log with the common base, which is the same base 3 here, and convert the subtraction to division. So I've combined and written them in this way. Right side, the same base 3 and 7 is as it is. Now 56 divided by 7 we can easily do, that is 8. So you have this. Now we are going to apply another property. The property is the one where you have log on both sides with the same base. The property of logarithmic equality. It says that if you have two logs on left and right side of the equation with the same base but different numbers, then the numbers are also going to be equal. So here you have log 3 8 equal to log 3n. Now here I had done one step which I didn't write because I thought that it is quite clear, but in case any one of you is going to get confused, I'm going to just correct that here. So what I did before I applied this formula was I took this here and took this one here. I'm quite sure you know why I did that, because log 356 and log 37 are like terms, whereas n is unknown, which we don't know. So I did this change before I applied this formula, correct? Now you can easily see log 3 both sides. This is actually n now. So here n will be 8. So that's your solution. That was first part where you solved. Second part is where you check your solution. So you also need to check, and that check you can do by substituting the answer you got. Do the substitution, n equal to 8 in the given equation which was given to you in the problem, and let's see whether both sides are coming equal or not. So I'm going to subtract them. This is the left side, LHS, and again we'll apply the same property that log with same base, different numbers which are subtracted changes to division. So 56 divided by 8, and that's very well equal to 7, which is nothing but the right side. So when I substitute, I'm able to check my solution and both sides are coming equal. So that's a correct answer. That's how you do question 27. Try question 28 similar. The next question that we'll work on is 32, and then similarly other answers I will provide you so that you can check your answer. So let's move to the next slide for question 32. Okay, let's solve this logarithmic equation now, and before we solve it further, let's see that both sides log have same base, so we can easily apply our logarithmic property of equality. And when we apply that, if both logs have the same base, the inside part is also same. That means x squared plus 2x plus 1, the one which was in bracket on the left, will be equal to the bracket on right. Now on the left is a quadratic equation, on the right is a linear expression. So let's take everything on one side. So I'm going to take now 11 minus x on the other side, and when it moves side, the sign is going to change. Let's collect like terms. 2x will be combined with plus x. This negative x, when it moves on the left, becomes positive. 1 will be combined with negative 11 because it changes sign accordingly. Now on the like terms, 2x with x will give you 3x. 1 with negative 11, it will be subtracted, so you get negative 10. Okay, now recall what is this equation. It has variable x and power 2. So can we say it's a quadratic equation? And every quadratic equation has two roots or two factors or two solutions. So now it remains to factorize this quadratic equation. So please find the factors for me. So what are the two numbers a and b which when multiplied gives you negative 10 and which when added gives you 3, the middle terms. This method is called middle term splitting. We've done a lot on factorization, so I will not go into much detail. But when you do the middle term splitting, you find the factors of negative 10. And definitely because of the negative sign, one factor will be positive, one will be negative. So what are the two such numbers? Okay, so tell me, can I choose plus 5 and minus 2? Let's see. So when we do that, we take the common factors. So x will go with x plus 5, negative 2x plus 5. So the two roots are plus 2 and minus 5. Now as promised, I'm giving you the answer key to check your solution. So this is the detailed answer key for question 27 that we solved. We had got n equal to 8, correct? Then for 28 you will solve yourself, that was homework. So it will be 2. For 29 it will be again 2. Remember to check your solution. Sometimes you may get extra roots, so we are going to avoid that. Following other solutions or the answer key for question 30 and question 31. Note in question 30, when you check for extra roots, one root is rejected. So only a equal to negative 25 is accepted because it satisfies the given equation. However, the other root which you got, a equal to negative 25 is rejected, and only solution a equal to 4 is accepted. So always check your answer when you have logarithmic equation. Sometimes you may have extra roots which you will reject. Similarly, for 31, you check for extra roots and only one root x equal to 2 is accepted. The other one, negative 4, is rejected. Very important. So following are the answer key for question 32 and 33. When we had solved 32 together, we had got two roots, x equal to 2 and x equal to minus 5. When you substitute to check for extra roots, both of them satisfy. Hence, we are confident in saying that both are the roots. Now, this is an important tip for your exam. If in your exam you get a multiple choice question where in one option is x equal to plus 2, second option is x equal to minus 2, third option is both a and b, and fifth option is none of the above. If you get something like this, then don't be in a hurry, don't do the question wrong. You will check by substituting both. The correct answer, as you see after substitution, is both a and b, so don't select only a or only b. In a similar way, if you get a multiple choice where one root is extra, you have to remove, then you choose only one root as the correct answer, not both. So that is an important point to be kept in mind. Similarly, solve question 33, check for extra roots. There are two roots you got, plus 10 and minus 10. Here both of them satisfy, so both are the roots of question 33. Moving further, I am showing you the detailed solution and the answer key of question 34 and question 35 and question 36. So double check your answers for extra roots. That's an important point not to be forgotten for logarithmic. You may write this as an exam tip. Check for extra roots for log equation. This is a very important point. Maybe you get 3 roots, 2 roots, but not all of them will be the solution if they don't satisfy. So that's what you need to check. Okay, let's do some more problems. Now we are moving to exponential equations. So the questions that we are now going to be covering are on page 291 of your math book, and these are on natural logarithms. Natural logarithms means you will take ln. Common logarithm means you will take log. So be careful. For natural logarithm, base is e. For common logarithm, the base is 10. That's the difference. Okay, so we'll be solving question 28. I'll pick up two questions here and one more. Let's pick this one. Yeah, so 28 and 29 classwork, remaining you will do yourself and check. So let's do answer 28. Very simple. You need to solve for each equation, means you need value of x, and additional you need to convert and round off to nearest 10,000. 10,000 means how many zeros? 4 decimal places. Okay, so here you will get your answer in decimal, and that's why rounding off is necessary. So we need x. So let's isolate x just like we do in linear equation and take other things on the other side. So this one is a number, like term is 11, so 11 plus 1 is 12. Very, very easy. So you need x. So what you are going to do on both sides, we're trying to isolate x, so divide by 2. So you get e to the power x is 6. Now this is value of e to the power x. We need the value of x. So therefore we have to go to log. So I will now take natural log of both sides. Ln e to the power x equal to ln 6. Now you need your calculator because ln e becomes x only. So your answer is going to be log 6. We will round it off as it will be a decimal on the next slide. Let's discuss in the same slide about question 29 also. So here again, like terms you will combine and isolate x. So e to the power x will be 18 minus 3 divided by 5. Now I'm just doing it quickly for you, which is 15 divided by 5 or 3. So you got e to the power x exponential equation equal to 3. X is in the power. This is a trick or a tip for exams. Very helpful when you have something of the form e to the power x where x is in power and x is what you need. Then you always take log of both sides. And because this is a natural logarithm question, we are taking ln. So ln e to the power x is ln 3. So this reduces, remember we have used the property that ln multiplied with e both are inverse, so is always going to be 1. Yeah, so this reduces to only x equal to log 3. So you can use down calculator or in exam you will be given these values for the ln6 and ln3. So just use them and don't forget to round off to 10,000 or 4 decimal places. So let's check our answers for all the problems now. Okay, so for the first one, 28th, we had solved it till this step. And now you use your calculator or just take the value and this comes out to be 1.7918. So 4 decimal places we have taken and this is an approximate value. This symbol shows it's approximate because it is going to be a very, very big decimal that we have rounded off. Next we did 29. For that log 3 we need. So ln 3 on your calculator would come out to be 1.0986 to 4 decimal places. In a similar way, check your answer for 30, 31, 32 and 33. Now we are moving to another set of important questions. Somehow I feel girls, one out of this, they are just going to change the numbers but will surely come for your exams. Here you need to simplify expressions with natural logarithm and this is on page 293 of your math book, question 46 and 47. I will just explain you one of them. That is 46 here. Very similarly, you can see the solution worked out here. So just remember, whenever you get a question where you have been written that write the expression as a sum or difference of logarithm or multiples of logarithm. So sum or difference means addition or subtraction, multiples means multiplication. So you are going to accordingly use that property of logarithm. For the first one, you have to use the sum or difference. So you will use the property accordingly, and for the next one we will see which property is going to help us. So let's see here, first question 46. Now you are given here natural logarithm. How you identify it as natural? Because it is ln, so it has base e. That's important. So it's given to you in a division form, questioned form. So therefore question property of logarithm is going to work, and the question property says that if you have questioned like 16 divided by 125, you can convert it into subtraction. So you write it as ln 16 minus ln 125. Okay, now because it clearly says write the expression as sum or difference, so you did difference here. I hope you can observe that you did subtraction and use the property of quotient. Okay, now these numbers 16 and 125, can we simplify this further? Definitely yes, because these are like perfect squares or perfect cubes. So 16 can be written as 2 to the power 4, 125 can be written as 5 to the power 3. So just apply that property here in this step. After that you have the powers, so 2 to the power 4 and 5 to the power 3. So next property you will use, because you saw powers, that's the hint or trick for you, is power property of logarithm. So let's apply. Again, you should remember that when you have log with a power, the power comes down. That's the formula. So I'm using ln a to the power m. Power comes down, so m ln. That's what is happening. So 4 comes down, 4 log 2 minus 3 log 5. So that's your 46 question. Let's discuss a little bit about 47 also. It's important. In 47, what is different? You have x cube and you have fifth power. So there are two power. Convert this radical to exponential and then apply power property. Okay, so let's now discuss some other important questions. This is from the different modules. So we are going to be looking at some formulas that we are going to be using for solving these questions. So first of all, I'm going to write those formulas for you that I'm going to be using here. Okay, so basically we'll be using one formula for exponential growth and one for exponential decay. So I'm going to write here exponential growth first. So if you see this word in your exam in a form of a word problem, you know the formula that you will be using is y equal to a multiplied with e to the power kt. And if you see the word exponential decay means decrease, growth means increase, then the same formula will work. The only difference is the sign. So negative kt, because this is decrease happening. Now y will represent the amount after t time has passed. A here for both the formula is same, which is the initial amount. It will be given to you in the word problem. T will be definitely the time. K here is the constant, and this constant will have a different name depending whether it is growth or decay. So if it is growth, K is the constant of growth. If it is decay, it is the constant of decay. So I'm just writing constant here, and then accordingly as per the problem we'll look at what is going to be the question. So the first question that I will be taking from here is on exponential growth. So we will try solve one question in this video together. That is question 11, and the second one I will take will be for decay. So I will take maybe say the next only. Okay, so let's do these two questions, and then 13, 14, 15 and 16 you will try yourself in your notebook, and then in the next slides to come I will give you the correct answers so that you can check for them. Okay, so let's solve question 11 first. We'll read it together, then we'll mark what is given and then use the formula. So Lucia read the population of a town has increased exponentially. So that's your keyword. It says very clearly increase. So this is a question on growth, and it also mentions exponentially. So you know you have to use formula number 1, this one that we've written. Now the current population of the town is this much. However, 1 year ago, so time here is 1 year, very clear. The population was this. So the initial population before 1 year, the one that we start with, A, is this, and the current population, which is Y, is this. So what is not given to you? You are given Y, you are given A, you are given T. The only thing not given is K. So that is what you need to find for sure. So there are two parts to this problem. Part A says, based on this information, write an exponential growth function. Let y represent the population after t years. So you need to write this expression, and formula 1 is to be used. Use the equation to estimate. Estimate means you have to give an approximate value, not the exact value of the population after 100 years. So for this part, definitely you will substitute t as 100. Unit is years. So this is a hint on the question. Let's now solve it on the next slide. Now that I've explained you all the things related to question 11, let's have a look at the solution. So for part A, you are using the same formula y equal to a multiplied with e to the power kt, and just you're substituting the values of y, a and t. When you do that, you are left with e to the power k value, which is the division of these two numbers. Now we need k, and k is in the power. So let's apply the property of equality for logarithmic equations. And the tip and the trick which I gave you tells you that if you need to find the variable which is in the power, take log of both sides. So I take here natural log of both sides and apply the property of equality, which gives you the value of k. So k, because ln e is going to be ln e to the power k is going to be k, because ln e is 1, right? So that's what we do here, and k comes out to be the log of this value. Use a calculator to plug in the value, and the k comes out to be approximately equal to 0.0198. So the rate of growth, which is your decimal of k, is this one. If you want to convert to percentage, just multiply with 100. So it is 1.98%. So look at the question in exam. If the option is in percentage, multiply with 100. If the options are in decimal, you choose the decimal. Okay, so you got your k, and now let's put everything back once more time in the first equation we started with. So part A had asked you, let me come back to this part, to write an exponential growth function, and that you will use as y. So formula, again we are writing one more time for growth. K is positive because it's growth. You put the value of A, which was the initial population given to you, K, which you have got here in the decimal form, and T. So the population of Lucia's town, T years, can be modeled by the equation. Now I didn't put the value of T here because the question says you represent Y as the population after T years. So we just keep it in the same way. Now for part T, we'll do the substitution. Part T says estimate, give an approximate value for 100 years ago. That means now we'll substitute T as 100. So substitute in the equation you got in part A, do the calculation, use a calculator, and this comes out to be 9304. Now, some of you might be thinking, what if the calculator is not there in the exam? How to do that? In that case, they will provide you with the log value. So they will give you what is the value of ln, this one that comes out to be 0.0198 in part A, and they will give you the value of the exponents or the log. Okay, so this is all about exponential growth. Similarly, exponential decay, the only change is in the formula. So for decay, as I told you, since it is decreasing, you will have the minus sign. Let's read this. So similar to a problem we had done in today's session on radioactive decay. That problem we talked about thorium, here it is cobalt. So it has isotopes, one of which is cobalt 60, it's a radioactive element, and it has a half-life of 5.7 years. So T, or the time, will definitely be 5.7. Here again it is half-life, so the amount that will be left will be 1 by 2a or 0.5 times a. You put it everything in this formula. That's an important formula to remember for you when it comes to exponential decay. Substitute, cancel the common factors, take the log. Again we are taking log, that's the trick, because the power has the variable that we need to find. So divide them, take the log. If you are allowed calculator, you can use that to get the value of constant k. If not, they will give you the value of log. So just divide them, and constant here, this case is decay, so rate of constant of decay or rate of decay for cobalt is about, if you say in decimal, 0.1216, 4 decimal places we've taken, or if you convert to percentage by multiplying with 100, it comes out to be 12.16 per year. So on this slide, I have solved in detail question 13 and 14 for you. Please check your answer, the reasons, the steps, the working, everything is given. So first you solve it yourself in your notebook, and then just use this answer key for checking your solutions. So I hope with that the module 6 of exponential functions that we dealt with today's session is clear to you. Please check your answers for question 15 and 16. These are the kind of questions you will be expecting in your exam. Already in this session I've given you the formula sheet for exponential growth and decay. Just remember, for growth it is positive, for decay it is negative. Solve all steps correctly, don't do a calculation mistake, and your answer is going to be correct. So that brings us to the end of today's math revision guide for module 6, and let's now see what is coming up next. For grade 10 series of revision going on, I will give you the complete math revision guide for module 7, rational function. So gentle reminder for all my students and all my viewers which are watching my videos and liking them, don't forget to like, share and subscribe to my channel, and hit that bell icon to receive all notifications of my upcoming video. So the next video in the series for grade 10 revision would be the part 2 for module 7, rational functions, and we'll cover the most important questions that will be useful for you for your coming exams. Good luck for your coming exams. Prepare well, study hard, practice more and more math questions, and wish you all the best. May you do well in your coming exams. So with that, we come to the end of today's session. This is Miss Ruchika signing off from her channel Mathematics Made Easy. Wish you all the very best once more, and don't forget to like, share and subscribe to my channel if you found this video useful. Give it a big thumbs up and put in your comments for any queries and questions for this session. Bye students.